So my research group has been using these ideas to try and understand variation, like the heartbeats in fractal patterns in animal behavior, all right? And I came up with this figure because I think there should be somewhere some level of complexity, which is the best case for some situation for an animal to behave, okay? And if it starts moving off to one side or to the other side in the behavior pattern, it's not really matching the environment anymore. And it could be a sign of a problem, like diagnosing a problem, all right? And so I'm interested in finding the Goldilocks zone. Everybody know what the Goldilocks zone is? In astronomy, it's Earth, okay? Earth is not too far from the sun. It's not too close to the sun. It's in the Goldilocks zone, all right? So planetary scientists are looking for planets in the Goldilocks zone. I'm looking for animal behavior in the Goldilocks zone of fractal complexity. All right. So how do we do this? I want to step back and get back to President Yamagiwa's talk, because if you want to study animal behavior and ecology, you have to get out to the natural world. So I've been doing that for the last 15 or 20 years, all right? This is a few images of me in Japan, actually, where I've gone to certain field sites, Yakushima, Koshima, to study wild Japanese macaques in their natural habitat and try and generate the complexity profiles. What is normal complexity for these animals, all right? And so that means you have to have close encounters with your study subjects sometimes. You might not be able to get that close, so you might have to do things distantly or remotely. You might be using technology like computers to help you collect data in the field, all right? Makes it easier. So sometimes we use direct observation like this, but other times we don't, all right? So the other half of my life is really about studying penguins, okay, around the world, in Australia, in Antarctica. And with penguins, I can't follow them into the ocean. So I have to find a way to study them remotely. And the way we do that is with biologging technology. We take these devices, which is smaller than a euro, we put them on the penguins, and we map where they are, what they're doing, what they're eating, that sort of thing, all right? And so it allows me to go to cool places like Antarctica and meet cool people, other scientists with similar interests, okay? And monitor animal behavior in some amazing places. But that's how we get the data from which we then start to measure complexity. And this might get a little bit complicated. I'm going to go through kind of quickly, but I want to show the process, okay? If we're studying animal behavior to generate complexity, we're going to start with our animal. Here it's the penguins, Adelie penguins. We get a dive sequence, diving, and penguins are binary. They're underwater or they're not. That's it, okay, as they go. We get a data structure of 1 and 0. We have a time series of 1 and -1, okay? Diving and surface, diving and surface. And because it's fractal, we want to change the scale and we want to measure it. So we measure it, basically we measure the fluctuation of behavior or the complexity at different scales, starting with small scales, going to larger scales, okay, doing the same thing, going to larger scales, doing the same thing. Very simple process with some difficult mathematics. And eventually, this line is telling us how complex the animal's behavior is, all right? Very simple process in the end. And I can use that measure for almost anything. It's the same as the fractal dimension. I can measure clouds, I can measure mountains, I can measure animal behavior, I can measure my heart using the same technique, all right? And this is what it looks like. It's a penguin diving and coming up, diving and coming up over a full day, all right? This is 5 different penguins doing the same thing. So they all have different complexity profiles, okay? And I want to use those to understand differences in their behavior. And ultimately, we're using this system as a way to understand how well animals are behaving in their natural environments, okay? if we know something about the environment, we'll know something about how good the behavior matches to the environment. And so I mentioned this complexity index, it can go up or it can go down. It can be moving animals or a time series, like behaving over time animals. And we can relate that complexity to like climate change, for example, human disturbance of habitats, animal welfare and animal health in the zoo or in a laboratory, or even in your home, okay? If you want to know if your dog is healthy, you can use these techniques. And especially how animals respond to natural challenges, okay? So these are a couple of my main collaborators in this. We're really using complexity to indicate some problem in the natural world with animals. And over the years we've learned a lot of things. For animal condition, you know, if animals like fish or mosquitoes, if they're being poisoned with some toxins, then they lose complexity. The fractal complexity changes in those animals, and we can see it. So we know there's something wrong with that animal, all right? For Japanese macaques and Spanish ibex, it's their general health, reproduction, parasite infection. It changes their behavior in a way we can measure using this fractal complexity. Dolphins are sensitive to human disturbance, okay? So their diving and surface behavior changes when there are humans around, and we can use that to predict how healthy they are in the environment. Penguins and Japanese quail are sensitive to stress. So we can detect stressed individuals by measuring the fractal complexity of their behavior. And if I put it all together, this is an example with Japanese macaques. You can see here, this is one sick monkey, and this is one healthy monkey. One day sick, one day healthy, the same monkey, all right? On the first day, not so much variability, okay? Not very complex. The pattern is very simple, and you know, the complexity score is like this. On the next day, very complex. A lot of change in behavior, okay? And timing of behavior. And in the end, very complex behavior sequence. And in the end, much more complex fractal complexity, okay? So we can use this measure to indicate the condition of the animal. But what does it mean for the environment? Another graduate student of mine, until recently, Xavier Meyer, who was working in France, was looking at penguins, and penguins in different colonies. This is Australia and New Zealand. And we're interested, how does the complexity profile change in those individuals? And what we see is that it does change across those colonies, okay? They don't behave the same way in each colony. And what we think is happening, so this is Penguin Island and Oamaru, okay? Not very complex behavior. And the water is not so deep. Shallow water, okay? So we think it's easy for the penguins to find food. And the food is evenly distributed in the environment, all right? But in Phillip Island, the water is very deep. It's dark blue here, it's very deep. And it changes a lot, okay? So it's harder for the penguins to find food. And we can see it. We can see it in the fractal complexity signature, all right? And it's interesting that if the penguins need, if they have high foraging success, it's very much related to the complexity, all right? So easier, like places here and here, where it's easier to forage, they have better success, all right? And the opposite is true for effort. If it's very hard to find food, they need high complexity, but they're not being very successful, okay? So I just want to highlight this complexity profile changes across environments, and we can use it to understand how well the animal will succeed in its environment, just by using this behavior sequence, okay? Or that's what we try to do, all right? And again, the whole goal of this activity is to use a very simple index of behavior from the natural world to understand how the condition of the animal and the quality of the environment, okay? This is work still in progress, but we've learned a lot of interesting things so far, and we're excited about the future of being able to use this very simple index to understand a lot more about complexity in the natural world.